Oi, decomposing the dark matter of sparse autoencoders. Very cool paper here today. There's been a lot of work on sparse autoencoders in the past, especially by Anthropic, showing us how we can learn about what's happening inside of our models using them. This paper draws a very interesting metaphor to physics that then does give us a pretty reasonable new thing to think about that I don't know if they actually named it in here. I'm going to call it dark representations as opposed to dark matter, but basically they figured out kind of what's happening to some degree in the remaining error left over by sparse autoencoders and shed light on new directions in the future that we need to take, and called out that we need something else alongside sparse autoencoders to give us knowledge on the non-linear part that those SAEs are not properly learning, right? So let's go ahead and get into it. Before we start, remember to like, subscribe, comment, share, all the YouTube things. Join the Discord server, follow on Twitter, connect on LinkedIn, support me either through Patreon or YouTube. For as low as $1 per month, you can get early access to my videos, or for a one-time payment, hit my Venmo. And if you'd like to borrow my brain for an hour or two, book a consultation call. All links are over on my Linktree. Let's get started. All right, before we start, there have already been two good questions asked by 8 Rice. First one is dark matter used in the literal sense in this title? The answer is no. I will hopefully explain that over the course of reading through the paper, and if I don't, I will hit it at the end of the video. And then the second one is, are scientists using metaphors in paper titles now, as in metaphor being dark matter? The answer is yes. I will definitely explain the whole metaphors thing and why that's okay to use in titles and in papers in general at the end. But let's, for now, just get to the actual paper. So, sparse autoencoders, right, are these little modules that we attach onto the backbone, onto the body of large language models, or really any other model you want to, where what they are told to do is you give them a vector within the model, and then you are they are an autoencoder, meaning they have to encode that vector and then decode it back into its original state. And they are sparse, which if they were not sparse, it'd be easy to do. They could just linear transformation it and then same transformation back, right? But they are sparse autoencoders, aka they are forced to use fewer values, fewer dimensions than the original input vector itself, right? And it's just a multi-layer perceptron, right? With in the middle a nonlinearity that is traditionally, I believe they used ReLUs. A better version I saw out of OpenAI recently was using just the top K values in that internal hidden layer of the MLP. But basically, when we do this autoencoding thing and keep it sparse, we can now say that every internal neuron of that MLP is itself very important in the reconstruction of the model's internal states, and therefore probably on its own, the sparseness forces each one of those neurons themselves to be represent a specific thing in the model that we can then hopefully interpret, right? This is all in the ideal behavior. And Anthrop has had some very popular use of these in the past. I should hopefully remember to link in the description. I have a video on said Anthropic paper in the past. But yeah, we when we have these sparse autoencoders, right, we can scale them to larger and larger sizes and end up with more and more little interpretable neurons that we can now use for interpretability sakes, right? And those are all great. And the two axes that we can scale upon are the width, aka the number of little latents, the number of variables in the hidden state, in the hidden layer of the MLP. And then as we scale that with those number of latents, we get a hopefully better and better reconstruction, which we measure in mean squared error. And we do find that it is actually a power law. As we scale up the width, the increase in reconstruction we get fits a power law, meaning just for the sake of this simplicity, you have to put more and more effort into getting fewer and fewer returns, right? Importantly, there is also a constant error term, so we never actually approach zero error. It's very obvious that when scaling, these SAEs bigger and bigger, that they are not approaching zero error, they are approaching a constant level of error that is above zero, right? So you'll be analyzing that constant error term and what is happening and what is the source of that error, right? That constant error term is a concern for the ambitious agenda of interpretability research because it implies that there are components of model hidden states that are harder for sparse autoencoders to learn and which might not be eliminated by simple scaling of SAEs. So as we scale SAEs larger and larger, they do get better and better, but barely, and there is this chunk of constant error term that is never quite just even chipped away at, like it's just always there. And so the goal of the paper today, the goal of this paper is to specifically study the error vector itself. We can see this being played out right here. So purple is the sparse autoencoder, and the x-axis is its width, and the vertical axis is the amount of the variance that is unexplained. Think of it as the error here, right? So as you get a bigger and bigger sparse autoencoder, you see this purple line goes down and down, but it only approaches the top of the blue section, right? Now, ignoring right now they have it separated into linear error versus nonlinear error. Ignore that for now. Just think of them as one solid block that is just constant error, unexplained constant error that is being approached but never broken into by the sparse autoencoder, right? So what we're gonna do, we already have our sparse autoencoders trained in these experiments. What we're gonna do is we're going to actually try and predict the remaining error that the sparse autoencoders do not cover. What we find is if we take just a simple linear probe, right? So it takes the actual input data, aka the model's internal states, and it tries to predict the error that is left over by the sparse autoencoder itself. We find it, in theory, when you try and predict an error curve, you should not be able to if your model is good. Your model should have only left the unpredictable part of the error if your model has the correct functional form to fit the data, right? What we find here instead is that this simple linear probe is actually very good at predicting the leftover error that is left over from the sparse autoencoder. And when I say extremely good, it's pretty crazy. Between 86 and 95% of the variance in sparse autoencoder error norm is explained by the optimal linear probe, meaning that like there's this big chunk of error, the error norm left over, and a simple linear probe can explain 86 to 95% of that error term, as in like this model, the sparse autoencoder is really not doing that well, to be honest. What we're saying here in terms of the actual graph is that when the sparse autoencoder approaches this asymptote, this horizontal line, the top blue and purple dashed line, that this separate model, the linear probe, can actually predict a huge chunk of that constant term that the sparse autoencoder is never quite getting into. And then next, so the previous thing we discussed was the actual norm, the error norm, right? So we take the actual error and we get I believe this is an L2 norm right here. Here, we're predicting the error vector itself, right? R squared here is lower, but still pretty good, between 30% and 72%, which so it's definitely lower than the prediction of the error norm, but it is still much higher than we expect. To elaborate more, remember, the error norm we described earlier is a single value, right? A single number within the real numbers, because when you take this initial vector of the SE error and you norm it, you're just getting its actual magnitude, right? And your regression style predicting regression from the input data onto that one single value. So our final output is within just the real numbers, a single number, right? Whereas here at the actual predicting the error itself is a vector, right? So therefore our linear layer is to be a d by d matrix, so a vector length by vector length, and then the final output value is itself a vector as well. And again, its prediction rate is still pretty good, although nowhere near as good as just the prediction of the norm. Now, intuitively, what this means, because linear terms are predicting the error rates, that means that there must be large linear subspaces that our sparse autoencoder is mostly failing to learn, right? Because these models that are learning this stuff so well are just linear, therefore they are linear subspaces. And for some reason, the sparse autoencoder is not learning, surprisingly, even linear subspaces, which are pretty simple to learn usually, right? Now, interestingly, so you can look at trying to increase the actual width and therefore number of activations that are like the actual width of the sparse autoencoder. And you can find that as you do so, the strength of prediction of the one that's predicting the actual error itself decreases. Whereas when you increase that width, the actual earlier, the prediction of just the norm increases. So when you make the sparse autoencoders wider and wider and less sparse, you actually get a result where it's easier to predict the norm of the error, but more difficult to predict the error itself. Very weird. Then we have some stuff left over after we try and predict the error of the sparse autoencoder, and some of it's linear. Fantastic. There's still some left over, right? And we're going to label this as nonlinear, because literally it is the stuff that cannot be predicted by a simple linear function. This is where we get that initial table. So this is the linear error, right? The part that those linear models could predict of the error of the original SAE. And then all the remaining stuff is what we term as nonlinear error, right? That's how we split these two up earlier. Whereas we previously discussed them as just one single constant of error that the SAE could never quite break through. And now we have separated that constant into its linear components versus its nonlinear components by using our linear predictors, right? Now, a third experiment, what if we have two different sparse autoencoders, SAE1 and SAE2? For a given input token, we can test how much of the variance in error norms in the second sparse autoencoder is predictable from the error norms in the first sparse autoencoder, right? So we take the error norm in the first sparse autoencoder at this, these are both the exact same token input stream, right? And we can take the norm of the error of the first sparse autoencoder and see if it is useful in predicting the norm of the error of the second sparse autoencoder. So what we're testing here, because we're assuming that the first SAE is smaller than the second SAE, what we're testing here is, okay, when we train a small sparse autoencoder and we look at its error, can we predict the error we would get if we were to go and train a larger sparse autoencoder? That's kind of the purpose here. And we do find that indeed per token SAE errors are highly predictable. This is nice because if you are looking to train some sparse autoencoders, you can first train some small ones and know that if you train 2, 3 increasing sizes or whatever it is of small ones, you will then be able to predict what error rate you would get if you would train an even larger one. So very, very good for deciding if and when, by how much to scale up your actual experiments. So based off these results so far, they're going to try and develop a model for what's happening, and they adopt the weak linear hypothesis, right? Which is a generalization of the linear representation hypothesis, the original one of which holds that, this new one, the weak one, holds that only some features in language models are represented linearly, right? So the sparse autoencoders grab linear features, and then also our little linear error prediction model grabs linear features, and then finally the leftover nonlinear error is nonlinear. Hence, the strong linear representation hypothesis cannot be true. We must grab the weak version hypothesis, which states that only some of the features are linear, right? If the entire model was linear, that'd be pretty crazy, in my opinion. I think it makes a lot of sense to say that some is linear, some stuff is linear, while some stuff is nonlinear. Makes way more sense in my mind. So X, aka our model's actual internal representations, is composed of a bunch of linear features and then a dense component, aka the nonlinear component, as well as any noise, right? Just anything that cannot be represented in a low dimensional linear subspace, basically. So if the model has some number of features and the sparse autoencoder has M latents, aka M neurons, in the center of the MLP, right? Then our sparse autoencoder can only learn the M most common features from the actual original model's internal state, right? And so our sparse autoencoder gets and learns all of those linear features, but only the M most common ones, whereas there are probably N total linear features in the actual model, right? So whereas the sparse autoencoder gets our first M most common linear features, we then still have left over that get put into the error term, the N minus M features which remain, right? As well as the dense stuff, all of the nonlinear and random noise, right? And that all ends up into the error term of the sparse autoencoder. And in this equation right here, it represents the removal of that original top M most frequent linear features by the sparse autoencoder, which removes them and leaves us with that error. Again, error really just at the end being composed of the nonlinear slash random parts and the less frequent linear features. And this explains why it's possible for us to actually linearly predict all of the error from sparse autoencoders, is because sparse autoencoders can only, if there are n total features of the model, sparse autoencoders can only learn the first m features, right? So therefore, this extra little linear model can predict the error of the sparse autoencoder using the n minus m least common linear features, and that is what we were learning here earlier. Sorry about the plane background noise, I apologize. Another way to say this is that we can predict error vectors because they consist in large part of not yet learned linear features, and that as we get larger and larger SAEs, we can predict a smaller percentage of the SAE's error because more of these previously not yet learned linear features can get learned by the larger and larger SAEs. Hence why our error term for our little linear probe on the predicting the SAE's error goes down. Or sorry, the R squared goes down when predicting the error vectors of the larger and larger SAEs. In some good news for the linear representation hypothesis, the norm of the model's internal state itself can in fact almost be perfectly predicted from that model's internal state. So remember, L2 Euclidean norm, right, is a nonlinear function. You square, add together, and then square root, right? But you actually can just take that initial vector and have a linear map that pretty damn well predicts that norm, which means, oh, all of the components in X must actually, not all of them, many of them, most of them, must actually be linear. So good news there, but not perfectly modeled, aka there is a remaining nonlinear component, right? Now, as a conclusion, the fact that SAE error can be predicted and analyzed at all is surprising. It's not until we made this model of, oh, actually the SAEs only predict the M most common linear representations that it starts to make sense, because now that we have a remainder of n minus m representations that are less common and therefore never learned by the SAE. So now we know in future studies that we don't just want to look at the SAEs, we also want to look at their error terms, right? And as I said earlier, we can now predict which tokens, or sorry, we can now predict the error rate of larger sparse autoencoders without needing to actually train them. We know how well they will do ahead of time, which can assist in our decisions as to whether or not to train them. And then it also implies that the presence of constant nonlinear error as we scale implies that scaling sparse autoencoders may not be the only or best way to explain more of model behavior. We need a metric that can somehow measure and help us look at the nonlinear components of model representations. So it's a call to action for a new thing to go alongside sparse autoencoders. Now, to answer 8 Rice's 2 questions, the first one is dark matter used in the literal sense in the title? No, it's not used literally. It is used, I think, well. I believe I skipped over the sentence that actually described it in here, but the idea, to my understanding, of dark matter in physics is roughly that there is, we have our current models of physics, and there is some error term, some unexplained component that in order to have all of our models make sense, we have to assume there is extra matter which we cannot see in there, right? And then the models make more sense. We call this matter dark matter because we don't actually have any proof it exists. We just know that our current models of physics don't work unless it does exist. Therefore, it must exist and we just can't see it, measure it, notice it for some reason. And then you go into like, oh, why can't we see it, measure it, notice it? It's because the theories or whatever, the hypotheses are that what do they call it? WIMPs or something, like weakly interacting massive particles, that these dark matter particles just do not interact with our own particles. They just are very weakly interacting. They just kind of sit there and they never do anything in relation to our matter. Therefore, we can't perceive them with ourselves. We have no way to interact with them, right? So the idea here being, okay, we have this error term, just like in physics, we have this error term that we would like to explain, and so we fill it in with saying, okay, well, first off, let's remove the linear part. We can now explain that. We can't interpret it because it's not interpretable with our new little linear module, but we do still have this remaining piece. We're going to call it our nonlinear error. You might say that this nonlinear error component down here could be called dark non-linear representations or something like that. Dark representations. So I wouldn't say there's actually dark matter. Obviously, it's not matter, it's representations, but we have in models dark non-linear representations. So like the dark term, so A. Rice just said he thinks it's close enough to the literal sense to be considered scientific. Yeah, like the obviously matter, there's not literally matter in sparse autoencoders, but there is literally a dark term, and just using the term dark matter as like a flashy title and then later introducing the term of dark nonlinear representations is what makes sense to do there, right? As well as the dark linear ones, right? So a non-metaphorical, non-flashy thumbnail clickbaity title might have said something like dark representation as opposed to dark matter, right? But totally fair to be a little flashy because the dark matter is a known term. And personally, when I'm reading through titles of papers and choosing which ones to actually read, if I see dark representation, I might just assume it's some other little subfield I don't care about. Whereas seeing dark matter, I wonder like, oh, should I read this? That's kind of interesting. What the hell's happening here? That's a physics thing, right? So I think it's fair. And then 8 Rice's next question was, are scientists using metaphors in paper titles now? And metaphors are used constantly everywhere. You just don't notice it. The way we learn is with metaphor. In order to, you've heard the term like standing on the shoulders of giants, right? There is like, you're not actually, there's nothing new under the sun. There's just combinations of old things, right? The way we learn and the way we build our models is entirely through metaphor to previously known things. That's all of knowledge. There is no like spontaneous, completely brand new thing. There is new data that we have to fit, and we do so by comparing it to old examples, aka metaphor. I'm totally fine using a dark matter connection metaphor here. Just yes, we should be defining a new term of dark representations or something, right? That's the whole gripe there, I guess. But totally fine in my minds to do it this way. Also wanted to point out there seems to be an independent Gmail author on this paper. Very, very cool. I might look into who they are and how they're working with MIT, that kind of stuff. I wouldn't be surprised if this person had been doing this and approached the MIT researchers and said, can you help me out on this kind of thing? That's super cool. But anyways, yeah, I guess end of video. Don't leave yet. If you got this far, you're going to love this video or this playlist. Don't forget to like, subscribe, comment, hit the bell, all the YouTube things. Join the Discord server, follow on Twitter, connect on LinkedIn, and consider supporting me monthly either through Patreon or by hitting that YouTube join button down below For as low as $1 per month, you can get early access to my videos. Or if you're a one-time payment kind of person, hit up my Venmo. And if you want to borrow my brain for a bit, consider booking a paid consultation video call. All of those links are over in my link tree. And yeah, end of video.